Dr. DeMott here, and welcome to Understanding a Function Pointer Overwrite. In this module, we're going to discuss various bug classes, particularly the basic stack overflow. Then we're going to go through a demonstration of how to exploit a function pointer. So there's lots of different bug classes, and the reason it's important to know about them is that once you've had an example and an understanding of how to exploit one particular class, then when you see that bug again, you can either make a determination, does it look exploitable, or are you actually going to exploit it? So things like the traditional stack overflow, function pointer overwrites, traditional heap overflows, off by ones, format string exceptions, uninitialized variables, integer errors, use after freeze, double fetch, type confusion. We're not going to cover every one of these bug classes in this course because that would take forever. Some of them have been covered in prior modules, at least talked about, and some of them we'll cover in this course in terms of how to actually exploit them. So first, let's talk about the traditional stack overflow, and then in the next module, we're going to talk about it even more and actually exploit it. For now, we just want to have a discussion about it because it was one of the most important bugs. It's sort of like SQL injection or cross-site scripting. It's one of these bugs that's been around for a long time, and it still plagues software today. So if you look at this program, you see that main takes a couple of arguments, argc, argv, env, some others as well maybe, but in this case we just have two shown, and argv represents input, so malicious user input. So you could suppose that this program is of any type. You could pretend that it's a network program or a registry key reader, or a file reader, something else, but for a simple example, a lot of times we have a little simple program like this. So argv represents our malicious user input, and the program represents something running at a privilege higher than yourself, like an SUID program or a network program that you're remote to, something like that. Otherwise, exploiting it wouldn't really make any sense, right? So we see that argv1, which is not the name of the program, that would be argv0. Argv1 would be the first parameter passed to this program, is passed to a function called foo. The function foo calls the parameter bar. We see a 12-byte stack buffer declared, and then we see bar used in a unbounded stir copy to C, which is the character buffer array. So what is that going to look like exactly? We know that that's a vulnerability. We've talked about that before. Let's just take a quick peek at that again. So we see that foo gets set up and pushes its first parameter to the stack, and then it pushes a return address when it's called. And then could be some other things like a stack cookie or a save base pointer. That's all we see here is the EBP, the save frame pointer, the 12 bytes of space, and the potential buffer overflow, so that when we return, instead of going back there where we should have, we could go anywhere. So that's the idea with corrupting a return address. And like I said, in the next module, we're going to look at that even more. In this module, I want to take a look at function pointers as we kind of baby step our way or work our way toward a full attack with shellcode and all of the things that go along with that. So in C, you may have a function pointer because it could be an index into an array of functions. So maybe we build a dynamic function pointer based off some base value or whatever. In C++, we see function pointers all the time in relation to vtables. So you have some pointer and it dereferences itself in some way to call other code. And if we could overwrite that, really bad things could happen, right? We could potentially call to arbitrary locations, which in a ROP exploit would allow us to do our pivot to start the ROP chain. And we'll talk about that in the last module of this course. For now, we're just going to call some function that already exists in the virtual space. We're not even going to do shellcode or anything like that. We're going to kind of take this first one easy as we write our first exploit here, and we're going to pretend that we want to call some other routine. Like, for example, imagine you could call the logged in routine so that you didn't have to call the login routine, something like that. So to help facilitate this simple learning exercise, I've got a program here. We see main, we've got some help usage stuff. If you don't put in the right number of arguments, that's what the argc is. The program wants two arguments, the name of the program and a number. And the number, argv1, is passed to foo. So when we look at foo, it ought to do some bounds checking on that argv1. Otherwise, we might have a stack buffer overflow, right? And we see a couple other functions declared, game, jackpot, foo, main. That's it. Now foo, when we have a look at that, we see that it changes the parameter argv1 to input. We see a function pointer declared, a 20-byte buffer, some random being set up. The function pointer is initialized to the function game, so that's the function pointer that we actually want to overwrite. And then we see stir copy input buffer. So that's where the overflow takes place. There's no bounds checking on the input into buffers. So we could do a whole stack buffer overflow and overwrite the return address and input shellcode and all that. But again, for this one, we just want to overwrite the function pointer. So then we see later in the program, the function pointer is actually called. So we could change that value to be whatever we want, and something else would get called. So a very simple view of the stack is going to look like this. We have the buffer, and we're going to go past the 20 bytes and write an extra 4 bytes and overwrite the function pointer. So that when the game is called, instead of saying, sorry, you don't win this time, that's typically what's going to happen when it checks our random number against the internal pick, because we don't have a good way of knowing it, although the random's not very strong and you could brute force it, or there's lots of other ways you could probably cheat this game. But for now, we really just want to focus on overwriting that function pointer. What we really want to have happen is that no matter what number we put in, jackpot is called. This is the magic thing we want to see. Jackpot. Congratulations, you win. Yay, we like to win, right? So, okay. How are we going to find the address of jackpot? And how will we overwrite it? That's really, and how do we automate that with Python? That's kind of all the things that we want to look at in this lab. So we'll use IDA and a debugger, of course, to both look at the vulnerability and find the address of jackpot.